Okay, let's start the second talk of this morning session. The speaker is Roman Gonin, and the title is Vertex Operators of Affine Quantum Groups versus Toroidal GL1 Algebra. Please.
Thank you for the introduction. Thank you for organizers of this conference, of the previous conference. I really enjoy my time in China. So also I want to say that I choose to talk about my old project because like since I was doing something which maybe not that related to the conference topic. Anyway, I apologize for those who already heard this story. All right, so I will start from uh, definition of quantum affine SLN. Uh, so okay, I choose. Wait. So I need a cyclic quiver with vertices labeled from 0 to n minus 1. And for each vertex of the quiver, I assign generators ki, ei, fi. They satisfy certain relations which should remind you ordinary relations of quantum group, but finite quantum group, but now we have labels in a cyclic quiver, and maybe relations the exact form of the relations is not that important. What I want to say is that we have Greenfield-Jimbecker product, which is determined in terms of these relations. So I can calculate the product of this ki, ei, and fi. And we have another set of generators, which are Greenfield generators. We have Greenfield presentation, which we had talks on Monday about it for Yangan, and now it's quantum affine. I'm not writing relations, but the generators are again ki, ei, fi, but now they have index k or m here. K is integer and m is positive integer, and the I, the label, the superscript belongs not to the cyclic quiver, but to linear line, the vertices labeled from 1 to n minus 1. And in Greenfield presentation, we have much more generators, infinitely many. And we have Greenfield's coproduct, which is written in terms of co-multiplying this kiz, eiz, and fiz. So these are two different coproducts, and this will be important for me in this story. Okay, now I define vertex operators for quantum affine SLN. They are intertwiners. So we've got, I don't know, it's kind of, how do you use it? Okay, so we've got Fi integrable level 1 representations of quantum affine SLN, and we've got Cn U, which is evaluation representation, and we can consider intertwiner from Fi plus 1 to Tenzorin on evaluation representation of Fi on the left and on the right. And since this is quantum group, it's different things. And we can consider dual operators, which are going in the opposite direction. And these intertwiners, okay, I can just, I denote phi epsilon k and psi epsilon k, these intertwiners which are evaluated on a particular vector from the evaluation representation, and I organize these operators as a formal power, is like operator valued formal power series. The same can be done for phi and psi without stars. So these are remarkable operators. Um, so as I promised, as I said before, we have like two different coproducts. So for Drinfeld coproduct, because we have explicit formula for co-multiplying KIZ, these operators actually have, there's a formula for them. They're exponentials of Heisenberg. And for Drinfeld-Jimbe coproduct, these operators are much more complicated. Some of them are also admit exponentials formula, but most of them don't. All right. So I will need parameters Q1, Q2, and Q3. The product equals 1. So Q2 is just square of the parameter of quantum group. And here appears some shift D, and my Q1 is like, okay, it's expressed through Q and D. Anyway, so a theorem says that there's representation of deformed W algebra of parameters Q1 and Q2 of SLN, and the representation is expressed via the vertex operators. So the formula like here, so we take Fi and psi I shifted by D, this parameter. And like surprisingly, you can take both Drinfeld-Jimbe coproduct and Drinfeld coproduct, and both options work. But like as I explained on the previous slide, these are different operators, and like it's not the same formula when you like substitute different vertex operators. It's like two formulas for they at the end of the day they give isomorphic representations, but like I don't completely understand why this happened. D, okay, D is just okay. It's just the matter of parameter. It's another. So deformed W algebra depends on Q1, Q2, and D is. Okay, when we had affine algebra, there was no D. Affine algebra depends only on Q. But if you go to if you go to toroidal, if you go to W algebras, you have two parameters. And the theorem says that yes, you can like, you take quantum group for Q, and then D is just a number. Could be any. Yeah, okay, and so this W algebra.
You just consider exponent with D coefficient of proportionality, right?
Say it again.
Psi 1 of dz. D is just an arbitrary parameter, right?
I mean, it's parameter which is expressed through Q1, yes, but it's a number.
So D exactly appear for the first time in this line Q1, right?
Yeah, like, yeah, it was also encoded in the Q1 appeared in relations of W algebra, which I don't.
So there are no so far toroidal algebra. They will appear later, right? D is just a parameter.
I mean, W algebra like are closely related to toroidal algebra, so in a sense, toroidal algebras already appeared. Yeah.
Okay.
So what I wanted to say is that if you use Drinfeld coproduct, then all of them are just exponentials, and this is standard formula for bosonization. But if you use Drinfeld-Jimbe, it gives you some other formulas, And also I was saying that like you've got the W algebra is presented through T1, Tn minus 1, and you can give formulas for them also, and you have to use not Cn, not evaluation representation corresponding to Cn, but to kth exterior power of Cn.
Do you have explicit formulas for T2, for T3?
Yeah.
For both coproducts, right? But
sure.
they will be different now, right? For different coproducts.
I mean, maybe we'll discuss it later. Okay, so toroidal GL1 is an algebra. So now I'm going to explain. We actually did not like. We rather work with toroidal GL1 rather than W algebras. So toroidal GL1 is a Hopf algebra dependent on two parameters Q1 and Q2. It's generated by certain PAB, AB in a lattice, and two central elements, C and C prime. For these generators, it has certain analog of PBW theorem, and it projects to deformed W algebras. This is the link to the previous slide. Toroidal GL1 has Fock module. So as a vector space, you just, the description is the following. You just take ordinary Heisenberg algebra and takes its Fock. And the representation could be determined as follows. You P0k acts as Heisenberg up to constant, and PK0 acts as McDonald operators. So we have the following picture. We've got like Heisenberg, which is vertical line, and we have McDonald operators, which are horizontal line. But there's another approach to this Fock representation. You maybe would like to consider green and yellow columns and write generating series for the generators from green and yellow columns. So there's another description of Fock module in terms of these generators from the first, zero, and negative first columns. Again, first column is just Heisenberg, and generating series for first and negative first columns are given by certain exponentials of Heisenberg. We can also, there's SL2Z action on this algebra, and we can consider for a representation of quantum-toroidal GL1 and sigma from the group, we can consider twisted model. It's like the same vector space, but we have new action. First we act by sigma and then act on the representation, or equivalently, like we're interested in these sloped generators of the toroidal algebra. This is version for toroidal algebra of the previous theorem for W algebras. Now we have to take the vertex operators for GLN, not for SLN. They're like differ by Heisenberg, but it's yeah. So analogous formulas which I had for T, I have for E and F from the toroidal algebra. No. Let me explain. So here I have these formulas. I take sum A minus B gives residue of n prime. So this representation depends on n prime. And if I take greatest common divisor of n prime and n to be 1, if they're mutually prime, then this formula gives a twisted Fock module as I obtained on the previous slide. And if I take n prime equals 0, then this gives this corresponds to tensor product of Fock modules or to yes, exactly. Any line any line has any line is a Heisenberg, but any like line which comes through zero. But any red line has like friends, green and yellow. And so this theorem describes the action of these red, sloped green, red and yellow lines. Okay. So how did we? Yeah, and the important point: these are operators for Drinfeld-Jimba comultiplication if they interested in any n prime. For like if n prime does not equal 0, for some reason we can't take just Drinfeld product. There's no formulas where E and F are just exponentials. It's like complicated. Okay, so how did we prove this theorem? We started from affine Schur-Weil duality. We take like tensor product of evaluation representation, and there's like quantum affine GLN and affine Hecke algebra acting on the same space. Okay, we can also take deformed antisymmetrizer and take like deformed exterior power. Okay, and the action of affine Hecke algebra can be promoted to action of double affine Hecke algebra by explicit formula, and like it's not unique. It's where n prime appears in the game. So now we've got like if we want this deformed exterior power, we still have action of affine GLN and spherical or antispherical Daha. And then we can take the limit n to infinity, like one have to take care taking such limits, but eventually we've got like action of two algebras, affine GLN and toroidal GL1 on this semi-infinite power, and this is the pair of actions from the previous slide. So I've got like two algebras acting on the same vector space. They do not commute. Actually, like this vector space is like if n prime greatest common divisor of an n prime equals 1, then this is a reducible representation for both of them. Okay, so yeah. It appears that these intertwiners are building blocks for action of toroidal algebras. You can now this is a story for Drinfeld comultiplication, and you can like it's theorem by I call proposition because it's technically very easy. It's just exponentials. So you can like for affine GLN you can express EI and FI like this through the vertex operators, and you can promote the action to toroidal algebras. But like I didn't draw it right, but here like n is greater than equal than 3. It's like toroidal algebras are a bit different for 1, 2, and greater than equal to 3. So here, like in the previous story, we have phi and psi to express the generator, and here we have either to psi or to phi. So I would like to understand, like it's a bunch of formulas. I would understand more about like how this some formulas work, some formulas written naively don't work. I would like to understand more why. So thank you for your attention.
Thank you. Any other questions, comments?
Okay, thank you. You see, just to clarify a little bit, so pretty much by definition, toroidal is the limit of spherical or anti-spherical data when n goes to infinity,
Yes.
right?
Yes.
They are dual to each other, but generally they coincide. In the limit, they basically coincide, right?
Spherical and anti-spherical are isomorphic for different parameters. This is what I use.
Right. But on the other hand, because of this, can you just spell your vertex anyway, Din-Kiyahara, your generalization of Din-Kiyahara, can you spell it entirely in terms of Daha parameters or elliptical algebra or whatever you like, shuffle algebras? Do you really need head-head, GLN head-head? Maybe you can just deal with elliptical algebra or Daha, spherical Daha or something. Why you need this GLN head-head? This is of course convenient because of many reasons, right? Pretty much the same story. You have Heisenberg's. Well, for instance, elliptical is very convenient to see Heisenberg's, right? Then you can just consider what vertex operators will be exponents of.
Technically for this theorem, I don't need GLN head. I don't need toroidal, but the question was, why do I need GLN?
You see, what are exactly these E and F, right? Directly in terms of elliptical, for instance, if your elliptical is more convenient for you, right? Do you really need the one head-head?
Like, maybe we should discuss this later. But
we will discuss it.
Elliptical isn't it just the same as toroidal one?
Okay.
Maybe we
Can you go to slide 6?
Slide 6. Okay.
One
yes.
before? One before, please. Yeah, this formula. So you say that it's worked for both coproducts.
Yes.
And so you know that they're connected by Drinfeld twist.
Yes.
I mean, two extreme coproducts, but you have many intermediate positions. Can you write some kind of invariant formula that works for any product that intermediate between, you say Drinfeld and Drinfeld-Jimbo one?
I did not thought about this. Maybe we should discuss it. Like, would be interesting.
Thanks. So on the slide 12, I think you described this nice proof using kind of affinized Chervil duality in the case of GL1 hat. I was wondering in the case of GLN or M hat, if you expect to have some similar kind of affinized double centralizer phenomenon, but now with like GLN, GLM duality?
But they in the limit they somehow coincide like a short theory. You can distinguish JLN and symmetric group. Pretty much the same.
So there's no centralizer theorem. Again, these algebras don't centralize each other, and they're like too big. And sometimes this representation is even like irreducible for both of them. So it's like very much. But there's like toroidal promotion of GLN-GLM duality, which like these algebras produce some integrable system. And these integrable systems coming from both of the algebras coincide.
But even for quantum group, Drinfeld duality here, they don't come with each other.
Right.
You know, more interesting, more complicated. Not semi-simple story. Right? Because the find
right.
You know this, right? Pretty much the same thing, but now down.
Double.
Any other?
I have two questions. You mentioned the deformed W algebras, and I wonder, can we do the similar construction for the deformed W algebra? Construct a similar representation.
Maybe I didn't understand the question, but like toroidal algebra, representation of toroidal algebra basically gives representation of W algebra of SLN or GLN. What's the question? Maybe.
Just yeah, you construct some you do some infinity construction for the toroidal algebra, and can we do some similar construction for W algebras?
But that is W algebra.
Okay.
Maybe I don't understand. Maybe we should discuss it.
We can discuss it later.
Yeah. Okay.
And the second question is there any connection between the deformed W algebras and double affine hack?
Between deformed W algebras and
double affine hack algebras.
Yeah. There is a connection, but in my understanding, like this toroidal GL1 and both double affine Hecke algebras and W algebras come from it through quotients, but they're like different quotients. And
okay, thanks.
So for that Schreiber duality, is there a type B version? So if you replace GLN height by maybe SON height, is there a similar duality?
Sorry. I mean, the question about GLN and SLN, right?
No. Replace GLN by ON orthogonal.
By ON, maybe you know better. Yeah, it's like, okay.
Okay, let's thank the speaker again.
Thank you.